Hi there, it's Professor Stevens. I'm going to do some examples for you from section 1.7, which is the section about solving inequalities. And it starts off with examples for involving linear equalities, which is basically what would look like a line if you were just graphing the equation. And they're fairly simple compared to some of the other examples. So I'm going to start with a few simple examples and then try to get to the ones that are more interesting and complex. So to start us off, I'm going to do exercise 17 from the back of the book for section 1.7. And so we're asked to solve this inequality, and what makes it an inequality rather than an equation is that we have an inequality symbol. And that's actually supposed to be a 3x. And so the directions are solve and write the solution in interval notation. Okay, so with an equation, particularly a linear equation, you would have one value to make the equation true if you have a solution. But with an inequality, you're going to have a whole section of the number line which would make the equation true, which we will write in interval notation, rather than a solution set with just the listed values of solutions. So first, I'm going to simplify by distributing the 3 multiplied times x and also times 5. And now I'll combine like terms. So I have 3x plus 16. And now that I have both sides of my inequality simplified, I'm going to set this equal to 0. So I will subtract 3x from both sides. And notice that my x terms completely disappear. So this thing is actually resulting in a statement that doesn't have any variables in it, which looks like this. So, what would the solution be then? What would you say x could be allowed to be in order for this original inequality to be true? Well, this inequality says that 16 is greater than or equal to 5, and that's true. And that, since we don't have any x values involved, we're not going to be ever plugging anything in. These are two constants that will not change. So when you see an inequality, or an equation for that matter, that reduces down to where you don't have any x's, that means that the value of x either doesn't matter at all because the inequality will always be true no matter what you plug in for x, or it means that there's nothing that could make the inequality true no matter what you plug in for x. In this case, since we have a true statement, that means that we could plug in any value of x, and as long as we plug the same value of x everywhere, when we simplify, we'll always get a true result. If this had been a false statement here, then we would say there was no value of x that would make the equation true. So that would mean it was no solution. But in this case, all solutions were all real numbers. So in interval notation, that looks like this. And that's our final answer. Okay, so those are all the values of x that would make our inequality true. So we'll go on and do another one. This time I'm going to do number 19. The directions are the same. We're going to solve and then write the solution set in interval notation. strict inequality this time, which means it doesn't have the equality part. It's not less than or equal to, it's strictly less than. That's what we call strict inequality. And I will do the same steps. I will first distribute the multiplication of 2x here. Simplify anything I can by combining like terms. And on each side of my inequality, I have simplified as far as I can. Now I will set everything equal to 0 by subtracting. I'll subtract 2x from each side. And that will give me, well, I don't need to cross that out. I'm just going to write that as 3x, which I wanted my blue back, 3x plus 2 is strictly less than 14. Then I will also subtract the 14 from each side and get 3x minus 12 is less than 0. Now you might have noticed that it might have been easier for me to leave the 14 on this side and bring the 2 over to it, because I'm going to end up working kind of backwards at this point. To solve for x. But I did it on purpose, and I'll explain why when it's relevant. So I get that x can be, x has to be less than positive 4 in order to make this equation true. So my solution set in interval notation would be that I can allow any value from negative infinity up to 4, but not including it. Now, that's how it's written in interval notation, but I do recommend that students try drawing a number line whenever you're doing a problem. The reason for that suggestion is that a lot of times students get mixed up when they try to do interval notation. And if you have your number line mapped out, for instance, like this, and then you try to illustrate what x being less than 4 would look like, it means you're starting at 4 but you're not including it, so that's an open circle, and you'd be going down towards negative infinity, right? So that approach, I believe, is really helpful in getting your answer written correctly in interval notation. All right, so now that we see our solution set, we should always check our answers, right? So we should really choose a value in that region between negative infinity and 4 and make sure that we get a true statement when we plug it in. So the easiest one in that interval is 0. So I'm just going to imagine putting a 0 here, here, and here. And so I would have my 8x term canceling out, my 3x term canceling out, and then I would just have the constant 2. And then the inequality symbol. And then putting a 0 here, I would end up with 2 times 7, which is 14. And this is true, which means that's one value in my interval I've tested, and I have a true outcome. So that's a good sign. And so I feel confident about my answer. There's something else I want to talk about here. Going back to the reason why I set this equal to 0, which in effect caused me to have extra work. And what I want to point out is that, yes, I could have come from this step, well, not from that step, let me do a different step, from this step, this one, yeah. So starting from there again, 3x plus 2 is less than 14. Rather than bringing the 14 over to the left side to set this inequality to 0 or less than 0, I could have just done this. Which would have saved me some writing and some time. Right? And it works fine. The reason that I made a point of setting the right side to 0 is because when we get to certain types of equations or inequalities that we're going to solve, specifically rational inequalities, it's going to be important that we set one side to 0 and move everything else to the other side. It's going to become essential to do that. And if you're not in the habit of doing that, you may end up doing something else which will cause you to get the wrong results. So I'm going to just form a habit here to always make one side equal to 0, or put all the terms on one side and nothing on the other side. As a habit, I'm just going to do it even if it does end up in more steps. I'm going to continue to do that so that I have a consistent procedure going forward. Now, I'll talk about it again. Why not now? Let's do an example in which if you were not practicing what I just described, you would possibly end up with the wrong answer. So I'm going to do now question number 74 from the book. And it's 3 over x minus 2 less than 1. So we're going to solve that, and then we're going to write the solution set in interval notation, same directions as before. But now I have a rational inequality. Rational because I have a ratio and there's a variable in my denominator. So if you were to do what most of us would do in this case, you would probably, actually this is not the one I would like to do that I think is going to be the most illustrative. Let me do a different one. Let me do 70, let's do 85. So this one is much more tricky. Okay, so what I might want to do here is just multiply both sides by the LCD. And that would cancel out on one side, and then I would have a new line, x plus 3 is less than or equal to x minus 5. Now what would happen next is if you went to set it equal to 0 at this point and started trying to move your x term over, you end up with both x's canceling out. And then you have a statement, 3 is less than or equal to negative 5, which is never true, which might lead you to say there is no solution, the empty set. So that's most likely what most of you would do, and that would be incorrect. The correct way is like this. Okay, so let me put a big, put a big thing here that's going to make sure we understand this is the wrong approach. So we'll do it again. The correct approach would be x plus 3 over x minus 5 is less than or equal to 1. And what I want to do is set this inequality equal to 0. Oops. So I'm going to subtract 1 from each side. And then, rather than just writing -1, I'm going to rewrite this with a common denominator. Then I'm going to combine the two fractions into one. Simplify. And then you see here the x's cancel out again. Positive x minus x. But now I have 3 minus 5, which is -2, in the numerator. What just happened to my nice thick line here? And then over x minus 5. And so at this point, I'm supposed to set both the numerator and the denominator equal to 0 to see which values would either make the rational equation 0, or rational expression 0, I should say, and also the denominator to see if there are any values that would make it undefined. And those are the two values that will divide up the entire real number line into intervals, where I might have values that would make my original inequality true. And what we call these are critical values. So I just wanted to first talk about how, or my rationale for wanting you to be in the habit of starting off by setting your inequality to have everything on one side and 0 on the other side. Establishing this habit might help you realize that you have to do that when it comes time to work a problem like this one. But now I'm going to backtrack a little bit and set us up with the overall picture and procedure of dealing with inequalities which have rational expressions in them, fractions with variables in the denominator. All right, so how do we approach solving the approach or procedure for solving inequalities with rational expressions in them, which for short we would just call them rational inequalities. Okay, so I'll just write that here, rational inequalities. Just like if it was an equal sign, we would call it a rational equation. Right, so we're learning an approach. Now the approach is this. Step number 1, move all terms to the left side so that only 0 is on the right side. Now, to be honest, you don't have to move them to the left. You could just say to one side, and then instead of saying have 0 on the right side, you could just say on the other side. Because it really doesn't matter which side you move all your terms to, just as long as all the terms are moved to one side and then 0 is on the other side. So step 2. Set, no. Ooh, I dropped my pen. you have to rewrite the expression, or I'll say the rational expression that's now on one side, having spatial issues, as a single fraction. So that you can then do step 3 and find critical values is a good heading. Find critical values of x by setting the numerator and the denominator to 0 and solving for x. 4, use the critical values to partition. The word partition means that you're going to use these critical values as dividers to partition the number line into intervals, or let me say it like this, to partition the number line and test values in each interval. Okay, those are the 4 steps. So going back to the problem I was working on, number 85, notice what I did. Number 1, I moved all the terms over to one side, and on the other side is 0. Then I rewrote my rational expression as a single fraction, right? And now I'm ready. That was step 1 and step 2, and now I'm ready for step 3, which is to find critical values of x. So step 3, I would set both the numerator equal to 0 and the denominator equal to 0 and solve. And so notice that if I set the numerator to 0 and try to solve for x, that's just not going to happen. -2, there's no x up there, obviously, and -2 will never ever be 0. So there's no critical value that I'm going to find using the numerator here. For the bottom, though, if I set x minus 5 equal to 0, I'll get x equals 5. So x equals 5 is my critical value. Also note that if I were to try to substitute 5 here, I would get -2 over 0, which is undefined, which means that my critical value will not be included in my final answer. My solution set cannot include the value of 5 because it would create an undefined result. So it is a divider. It's going to divide up my number line, but it is not a value that I would include in the solution set. All right, so now that I've got my critical values, I'm going to do step 4 to partition the number line and test values in each interval. So with my critical values, 85 continued, I have critical values, just one, x equals 5, which means that my number line, if this is 0 and this is 5, I could partition the number line with 5 being my divider. It's an open circle, which I'm not going to include in my solution set, but I might be able to go this way, and I might be able to go this way, right? So the intervals that I will be testing will be from -∞ to +5, not including it, and also I'm not going to put the union yet because I'm not sure if both intervals work. And I'll also be testing from 5 to positive infinity. So I'm going to choose a test value in each section. So I'm just going to divide it up into two sides here just to organize my work. So for this side, my test value, I'm going to use x equals 0. That's an easy one. On the other side, I'm going to use, I don't know, I'll just use 10. No particular reason, except that 10's a nice number sometimes, can be a helpful number in certain scenarios. So I'm going to use my test value of x equals 10. Now I have to use my original inequality to see if I get a true statement using each of those x values. So my original inequality was x plus 3 over x minus 5 less than or equal to 1. Now when I plug in 0, what happens? I get negative 3 over 5 is less than or equal to 1. Is that true? Yes, it is. Okay, so because that's true, that interval is valid. Now I'm going to do the same thing on the other side. I'm going to do x plus 3 over x minus 5 less than or equal to 1. Plug in my test value. And now I have 13 over 5. Is that less than or equal to 1? Well, no, because 5 can go into 13 more than one time. So this is not a true statement. It is a contradiction. So I will not include this portion over here. I will not include that in my final solution set. So the answer for number 85, my final answer, so for 85, the solution set is in interval notation, negative infinity to 5, not including 5. Okay. So that's how you handle one of those. And those are the trickiest ones, I believe. So if you can handle that, then you'll be okay for the rest of them. But in general, if it's not a rational equation, if it's just, or a rational inequality rather, if it's one that is linear or quadratic, you're going to solve those the way you would solve a regular equation. Except for a couple of things. So I'm going to go through a couple other examples here. Let's talk about solving, actually I think I'll start a new video. So this one will just be about how to handle a rational equation in which your x's could cancel out if you try to use the clearing fractions method, right? So that is what would have happened. Let me just refresh your memory. Remember I said the wrong approach, which is our normal approach. If it's an equation, we would try to clear the fractions first by multiplying everything by the LCD, which actually cost us information. In the situation where it's an inequality and not a regular equal sign, this is the wrong approach because we lose information that way and we end up with the wrong result, right? So we would have ended up with no solution doing that, whereas the answer was supposed to be from negative, all the way from negative infinity up to 5. Any value in that interval works for that inequality. So that's what this video is about. Watching out for that pitfall, and I will do a separate video where I'll work out some other examples, such as solving an inequality with 3 parts, and also solving a quadratic inequality. Thanks for watching. Take care.